There are only two objectives in this section. Estimate a limit using a numerical or graphical approach. Learn different ways that a limit can fail to exist. Look at this function. To sketch the graph of the function, f(x) equal to x cubed minus 1 divided by x minus 1 for value other than x equal to 1. This function is defined for all the x value f set x equal to 1. You can use standard curve sketching technique. At x equal to 1, it is not clear what to expect. To get an idea of the behavior of the graph of f near x equal to 1, you can use two sets of x value. One set that approaches 1 from left, and one set that approaches 1 from the right. Look at the table below. The x value. Set the x value approaches 1 from left, and set the x value approaches 1 from right, and calculate the y value. There, from the table, we found that the f(x) approaches 3 from left, and also the f(x) approaches 3 from right. The graph of f is a parabola that has a gap. Here is a gap at the point 1, 3. Although x cannot equal to 1, you can move close to 1. As a result, f(x) move close to 3. Using limit notation, you can write limit f(x) x tend to 1 is equal to 3. This discussion leads to an informal definition of limit. If f(x) becomes arbitrarily close to a single number L as x approaches C from either side, the limit of f(x) as x approaches C is L. This limit is written as limit f(x) x tend to C is equal to L. Look at the example. Evaluate the function f(x) equal to x over radical x plus 1 minus 1 at several points near x equal to 0, and use the result to estimate the limit. This is a function, and based on the question, we put the limit and estimate when x near to 0. You can construct a table, set the value of x approaches 0 from left and from right, and we calculate the output, the f(x) value, and we found that the f(x) approaches 2 from left and also from right. From the result in table, you can estimate the limit to be 2. This limit is reinforced by the graph of f. Look at this graph. This is a graph. And look at the when x equal to 0. The f is undefined at x equal to 0. So the limit of this function as x approaches 0 is 2. For the second objective, look at this example. Show that the limit modulus of x over x when x tends to 0 does not exist. Consider the graph of the function. From the definition of absolute value, the modulus of x can be written as piecewise function. And for when the x is positive value, when x greater than 0, the value is 1. And when the x is negative value, after we simplify, there is negative 1. So look at the graph. Fx is equal to negative 1 from negative side when the x less than 0. And the fx is equal to 1 when the x is greater than 0. So limit fx when x tends to 0 does not exist. So no matter how close x gets to 0, there will be both positive and negative x values that produce fx equal to 1 and fx equal to negative 1. Specifically, if delta is a positive number, then for x values satisfying the inequality, the modulus of x is between 0 and delta. You can classify the value of modulus of x over x as follows. For the negative x value, so it's between the negative delta and 0, the function produces negative 1. But for the positive x value, from 0 to delta, the function produces 1. Because function approaches a different number from the right side of 0 than it approaches from the left side, the limit of this function does not exist. Look at the properties here that the limit fail to exist. The first one, the ff approaches a different number from right side of C than it approaches from the left side. Fx increases or decreases without bound as x approaches C. Fx oscillates between two fixed values as x approaches C.